So I'm going to do hopefully quite a short video on indicators and highlighting what you need to know about indicators, what we need to know about endpoints and what we need to know about equivalence points, and knowing that those things are not the same. There's limited detail to what I can go in a short video, so do read textbook on this, I would suggest. But a few key ideas for you. The first of all is that indicators are weak acids. Right, so in other words, they've got this reversible reaction between the weak acid, H+, and the conjugate base. Now the indicator H-ind, the weak acid, this being the H that can be lost, would have one colour, and the conjugate base would have a different colour. So this negatively charged species would be a different colour to the acid. Now this is a reaction that's at equilibrium, and so it would respond in the same way to any other reaction at equilibrium, according to Le Chatelier's rules. So in other words, if I add H+, the equilibrium would shift to the left. In other words, if I were to add a whole load of acid to this solution, H+, it would shift the equilibrium towards the protonated red substance, making it appear as a red colour. If I were to remove H+ by adding alkali, the equilibrium would shift to the right, making the substance blue. This is just a made-up indicator represented by H-ind, and this is the generalised term for indicators that you're expected to know. The point at which the colour changes from red to blue is called the end point. That's the end point, the measurable, seeable, if you like, end point of the reaction. You can see a change in a titration when it goes from red to blue, or pink to colourless, or colourless to pink, or red to yellow, whichever indicator it is you might be using. Right. You don't need to know any specific indicators. There are a list of them in the data book and you should refer to them. But you certainly need to be clear on the idea that the pH of the end point of an indicator, i.e. the point at which it changes colour, say from red to blue or blue to red, is approximately equal to the pKa value of that indicator. Now let's think about that for a second. So here we are. That equilibrium reaction would have a Ka associated with it, and so the products over the reactant. Now if you've got it moving from red to blue or blue to red, you would have a roughly equal concentration of the product conjugate base and the acid. In other words, the concentrations of that and that are the same, more or less, at the end point, the point at which your colour changes. And so at that point, so Ka is equal to H+, or in other words, pKa is equal to the pH of the end point is roughly equivalent to the pKa of the indicator. It's sometimes called, in certain textbooks, it might be called pKin. You might sometimes see it called pKa, so the IB seem to be calling it. Let's just be clear for a moment. If this was a titration reaction, this would be the volume, say, of, this would be the pH of the solution, and this would be the volume of, in this case, looks like a strong alkali being added to a strong acid. The equivalence point, this is the volume of the hydroxide being added, sodium hydroxide, let's say. The end point is the point at which it changes colour, but the equivalence point is exactly this point here on the graph. So in other words, the volume at which you've added in this titration the same number of moles of, say, the HCl and the sodium hydroxide. So the end point and equivalence points might be the same, they might be very similar, but they are not defined as the same thing. So the end point is the point at which the colour change happens, end point is the point the colour change happens for the indicator, and the equivalence point is technically the point at which you've added the same number of moles of acid and alkali. You need to know the difference between those two, so make sure that's on a flashcard that you're learning and practicing. You also need to be able to select an appropriate indicator for a particular titration. Now for strong alkali being added to strong acid, most of the indicators would do. You want to choose an indicator for which the pKa is at about the middle of the sharp point of the titration. So we get this sharp increase in pH in this example here, and that will be at around about pH 7 for strong alkali being added to strong acid. So you want an indicator which has got a pKa, or a pKin if you like, of around about 7. Okay, for the reasons I talked about before. The point at which it changes colour are around about that range there. If, for example, I'm just going to draw another picture. I haven't drawn a very sharp upward bit here at the equivalence point, but never mind. So this would be a strong alkali being added to a weak acid, and the graph has this kind of shape. Remember the whole thing about the buffer region. That's what you need to spend time on it, and the half the equivalence point is equal to the pKa of that weak acid. But anyway, in terms of selecting an indicator, the equivalence point, the sharp peak, the sharp increase of the graph happens at the equivalence point, and the centre of that is around about 9.5 pH. So you want an indicator with a pKa of around about 9.5. And a good example one there to use is phenolphthalein. And phenolphthalein will change colour. I'll have a different colour down here than up here. So when you get to that point there, which over a very small volume, it would go from being colourless to pink, because it's going up very quickly over a very, very small volume. So here's an example question where an acid-base indicator, phenol red, which we're calling HIN, changes colour from yellow to red as you go from acid to alkali, but specifically over that range. So which statement is correct? We're going to go through all of these in turn. In strongly acid solution, the concentration of HIN is much less than our IN minus. Let's think about that. So in strongly acid solution, we'd have a high concentration of H plus. That would shift that equilibrium to the left, meaning that would be much higher than that. So that can't be true. The pKa of that indicator matches, yes, it is within the range at which it changes colour. So that's right. So that should be the right answer, and it is the right answer. So the pKa is going to be kind of usually roughly at the midpoint of the range through which it changes colour. The IN minus ions are yellow. Let's think about that for a sec. Well, we know here that in acid it's acidic and it's red when it's alkali. So when it's acidic, it's yellow. We've already said that when it's acidic conditions, it's going to be over to the H inside. So the yellow must be the H in. So that can't be right. Just going to go through that again. So we know that when it's acidic, it's yellow at 6.6 and below. And we also know that when it's highly acidic, we've got a high concentration of that. The equilibrium lies to the left. So this stuff must be yellow and this stuff must be red. We can work it out from here. So that can't be right. And we know it's not anyway. Phenol red would be a suitable indicator for strong acid, weak base. Let's consider that for a moment. So strong acid, weak base would look something like that, I guess. So pH 14 up there, that might be pH, I don't know, 11 say, pH 7 there, and the equivalence point pH is going to be around about 5 or something. In other words, below the range of the indicator given, so that won't be any good either. So hopefully that helps with selecting of an indicator. Here are a couple other multiple choice questions for you to look at. Have a look at those, and I'll point to you page 720 in a second. Have a look at those, see if you can answer them. So question 52, well, none of those first 3 points make any sense at all. The only one which is clear is D, so the pKa range of an indicator is within its pH range. And the next one, bromocresol green, has this range. We'll have a look at part A in a second, and we look at those those graphs. So it's got a range of 3.8 to 5.4. Which titrations could we use that on? What would be a suitable, a likely pH for that indicator? Well, midway between those two numbers, whatever that is. So 1.6 difference between them. So let's say 4.6, something like that. And what color will it be at 3.6? Well, it's below 3.8, so it's going to be yellow, isn't it, at that pH? But now let's look at those graphs on page 720. Hang on a second. I think it means 721. So here's the table it's referring to. So the pH range was 3.8 to 5.4, and we said the midpoint might be about 4.6. And so the pH range at equivalence, well, it has to be either this one or this one. So that midpoint, so 4.6, whatever it was, falls within here and this range. So you could use that indicator for strong acid, strong base. You can use most indicators for that actually. But then strong acid, weak base will work because the range at which the color change can happen, or the pH range at equivalence, the point at which the graph is steep, is there. So the indicator will fall within that range. And this one won't work because that range of through which the indicator changes color is outside the range at which the pH the pH changes sharply in the titration. Hopefully that was useful. Let me know if you need more.